Okay, welcome back. So this is about quantum computation introductory session on this. So if you can write in the chat also that if you have there is prior idea or how actually do you feel about learning this Qiskit and quantum computation. So you can write your experience or your feelings here in the chat of Google Meet. So actually, we know that is our where we live. Actually, this is actually our classical system. But now we are actually learning, as Sir has also mentioned, that we are at the beginning or on the verge of the new revolution. So here actually we'll be discussing the new thing. It's actually not what we are familiar with. Here we know that is, for example, if I give some example like say gravitation. So uh, we our Earth revolves around the sun. Okay, so gravitation law, Newton's gravitation law, you all know, but actually it fails when in the subatomic scales, right? So that actually comes from there. There comes several new domains of physics. Then quantum mechanics also one of this branch. But here we are not going to discuss thoroughly of quantum mechanics. Rather, we'll be focusing on quantum computation and only very simple mathematics regarding this. Actually, information is processed in atomic or subatomic level. Here we are going to discuss and why quantum computation is actually very much popular. In this entire workshop, it will be clear to you when we discuss the quantum algorithms also. And classical algorithms are there and the corresponding quantum algorithms. How actually quantum computing algorithms they performs better than classical algorithms, then that will be learned. But whatever, what is actually quantum computing? What is classical computing? Classical computing means we exploit the phenomena of our classical physics. Here also in quantum computing, the computation means any operation that you also do. Suppose you are adding two numbers, this is also operation. So any computation which actually is performed based on the quantum mechanics phenomena. Some quantum mechanics phenomena that, of course, I will be not discussing today. That will be discussed on day 3. These are superposition, quantum entanglement. I will just mention quantum superposition later. So some quantum phenomena are there, quantum mechanics phenomena. So these are exploited to perform. Now, coming back to the basic unit. So because we have to learn something that is like quantum algorithms and how we can use those quantum mechanics phenomena. So start from the very beginning. So just like when we are trying to build a house, so we need some bricks, right? So here, the brick is here quantum bit, just quantum counterpart of classical bit, right? What is classical bit? So you know, it is 0 or 1. Uh, you can say that is switch. In case of switch, we know switch is on, switch is off. There may be multiple states, but generally we, in terms of switch, we can see 0 or 1. In case of quantum computation, here physical implementation is actually it is uh, physically implemented. Actually, we have to uh, design or physically implement qubits. Like IBM also designing qubits. Also other tech giants, Google, Amazon, they are also designing uh, qubits. So how actually these are designed? So with the polarization, nuclear spin, and electron spin. Suppose electron spin, these terms are actually uh, all of you I think familiar with in 10 plus 2 level. So suppose electron spin. So spin up, spin down. Say spin up is 0, then spin down is 1 state, like this. So we can represent. Now, then how the qubit is a system. Okay, the quantum state of a qubit is represented using Dirac's notation and Bloch cycle. So now I am coming to this. Before this, let's do some mathematics, bracket notation. So let's do some mathematics here. So how we can represent this. Well, so first of all, again, I will start with classical information. And we are starting with single state here. Single state. Say for in case of classical, it is 0 or 1. So I am starting with classical information, right? Classical information. Now say a system, take a system. Suppose switch of a fan. Say X is a system. If it is a switch of a fan, then how many states are there? Can anyone tell me? You can unmute yourself also. High state, low state.
Two.
Yes. And suppose I am explaining it in detail, medium or then off. So maximum 4 states. You can see this is actually here a general way of representing this. So these are the set of states. So 4 states can be there. Take an example of die. So how many states in case of die? 1, 2, up to 6. 6 states are there. Now, if X is a bit is a system, classical system, bit. So, you know, the state is 0 or 1, right? So, this is a system, bit is a system, a die is a system. So, here actually we are mainly focusing on bit. So that we can learn qubit later. Bit, so the states are 2 states are there, single state I am talking about, 0 or 1. Okay, these 2 states are there. Now, here, next I am going to write a notation which is known as Dirac's notation. Dirac he was a mathematician.
Good evening, Sumanta. This might answer your question. I know.
Sorry for the interruption. Yeah. So here, first I will show you column vector notation and then row vector. Okay. Say, um, for example, it is a state. So this is say 0, 1 state. So 0 state actually it is in the column vector. This notation is used. Dirac notation is this, and this is row notation is this. This notation is also known as notation, and this is known as Kate notation. Fine. Uh, just give me a second. I'm just resharing. Just just a minute. Okay. That has okay. So yeah, I'm resharing it. I think again you can see my screen. So these notations actually known as Dirac's notation. So column vector of say 0. So in general, so again in the next slide I'm discussing. So how to represent this column notation and this say this. So in case of say the system is bit, so let me write down for your understanding 0 and 1. These two are states. Okay. So uh, for this case, say if I write the column vector for 0, how this column vector can be written? So I am writing this definition. So column vector, no doubt about it, this, sorry, alpha is a column vector. So you have to put 1, you have to put 1 in the corresponding state. In the corresponding state. So this is the column vector. So the actually there are two entries, for 0 and 1. So for 0, we have to put 1 and rest will be 0. And the rest will be 0. Put 0 for the rest. Okay. So now for 1, tell me what it will be. There are two entries. So for 1th entry, it will be 1 and this is 0, right? So now I think you can, you can tell me in case of die, where the states are like this 1 to up to 6. So how 1 can be represented? So if there are 6 entries, so first entry will be 1, all other 5 entries, remaining 5 entries will be all zeros, right? Now this is about column vector. Now what is row vector? For example, this corresponding row vector is actually, you can understand this is row vector 1 0 is row, and for 1 this is 0 1 as simple as. So we have understood column vector and how to represent, and we have understood row vector how to represent it. And what are the names? The Dirac's bracket notation. This is actually, again I repeat, this notation and this notation. This is Brad notation and this is Ket, K-E-T, Ket notation. Okay. So fine. Next, we'll show some more operations like multiplication. Say there are, this is say A, okay, this is a row vector and this is column vector. So how to multiply this? So if I write this, that is there, this type of multiplication we are discussing it. Say in place of A, I am writing in place of A, I am writing here say 0, and in place of B, I am writing here 1. Okay. So what will be this multiplication? So actually you have to multiply 0 with 1. So what is 0? Row vector 0. Row vector means 1 0, and then you have to multiply 0 1. Just tell me, anyone tell me what is the result? This is a normal multiplication that you have done. So this way and this way. What will be the result? Tell me. It will be. In the meantime, I am writing this one also for you. So tell me the answer. And one is row vector for 1, 0 1, and 1 0. What will be the answer? Any response in the chat? No. I think you can understand the multiplication here. So this 1 is multiplied with 0, 0, and plus 0 is multiplied with 1. So this is actually nothing but 0. Now tell me here, again it is 0. Again it is 0. Now if I write like this, so what will be the result? So I will give the answer of here, but here I think that question may be given in your assignment, because today some simple questions will be given to you. so that you can do solve it within 24 hours. So anyone there who is going to answer this product? So this product is known as this inner product. Okay. So I'm giving you one hint. If A and B are equal, they are you can see they are different. So when they are different, it is 0, and when they are equal, it is 1. So of course the answer will be here 1, but I think you have calculated it. 0 0, that is again I am writing here 0, sorry, for 0 1 0, and it is again 1 0. So you can understand 1 1 is multiplied, then it is 1 only, and similarly for this also it is 1. Okay, so if you remember this thing, so you can easily understand what is the result of this inner product. Now come back to this next, another multiplication. So these notations are should be actually useful for you. Why will be writing this, and not only code. So what we are going to code. So because some gates. So gate representation. If you cannot understand this, then it will be difficult. So first, next is another product. So let me write first explain the product here. Say, uh, sorry, this is Kate and Brad of C. That is, I can write multiplication of column vector and row vector. Just like here in the previous slide. So this is the multiplication of row and column. This is now column and row. That's the reverse. So what will be there? So it's very simple. So this is a column vector. So 1 0, and again for 0, but it is row vector 1 0. So what will be the result? So you can see, okay, one thing I think it's clear. So this you can write also here with this, okay. 1 0 can also be written as like this, okay, no problem. Now 1 1, right? So what is the result? Here actually 1 0 and this 1 0. So this is 1, okay, and next is 0 here, 0. Next is here 0 0 1 0, and then 0 0, right? So you can see in the previous case, in this inner product, if we multiply two vectors, then that is first row, then column, we are getting the dimension count is scalar. We are getting some scalar value. Okay, some scalar value is the output. Scalar is our output here in this case. But here actually dimension is actually increases. Here it is known as this multiplication outer product. There is also another product is there, but today it is not going to be discussed, tensor product, but only inner product and outer product is actually I have explained here. Now here you can see, so we can give you the task here. So 1 and say 1 also. So what will be the result? What will be the result of this? So I can give you the formula, this, that will be helpful for you to answer. It has 1 only in AB entry and 0 other and 0 elsewhere. Okay, so this is actually here 0 0 entry, right? This is actually 0 0 entry. So here only one, rest is 0. So here, so you can simply write. So you know this is actually row vector, and this is sorry, this is column vector, and this is row vector. So here the dimension will be 2 cross 2. And in which position 1 will be there? 1, 1 position. 0, 0, 0, 1, 1, 0, 1. So here 1. So rest of the position will be 0. So is it clear, I think? So if any question given like this, so you can correctly choose the answer. So next I am coming to now, this is classical I have discussed. The state X is a bit. If I discuss quantum system, quantum information or quantum system, previously we were discussing classical information. Thus the operations, the performance of these all operations are same here. Here X was bit in classical in the previous slides. Here I am telling you this is cube. But number of states again 0 and 1. Now what is the difference? Just I am coming back to this 0. But the number of states is 0, 1. That is this uh, here. Say, sorry. So this is one state and this is another. So that means quantum state is represented by a column vector. Okay, and this 0, 1, just like classical 0, 1 are actually these are known as standard basis vector. These are vectors, column vector, and known as standard basis vector. Why standard basis? Because say there is a vector like this. Now this vector can be expressed in this way. Okay, say 1, 0 plus 1, 4, 0. Okay, so what is 1, 0? 1, 0 is nothing but column vector 0, and 0, 1 is nothing but column vector 1. So that means vector, any vector, any vector can be expressed in terms of those standard bases. 0, 1, 0, 1 here. So this thing is 0, 1, this column notation, column vector notation is clear. So now one more thing is clear, that these are actually standard basis vector. And quantum state, there are two actually states for qubits, 0, 1, and a difference is there. So now I am going to discuss here in the next slide. Just a minute. Okay, so here we can discuss this thing. So what is, say, quantum state? So any quantum state actually represented using column vector. So suppose psi is a general state, quantum state. Okay, a general quantum state psi. Okay, so this is a vector. So this can be represented, again, any vector can be represented in the, as mentioned in the previous slide. Any vector can be represented with 0, 1. So it is, say, alpha 0 and, say, alpha 1. Now, what is the difference between bit versus qubit? Okay, so let's come back to here. Actually, here we have told you that the quantum bit is a quantum mechanical analog to classical bit. So in classical system, we know the system can be in either 0 state or in 1 state. Okay, so this actually here any state, say, any state is there. So it is represented, just let me write, it is represented with 0, and 1. So it is also represented with this same way. Okay. But here one thing you can mention, it is actually it is always alpha I is complex number. Do you know what is complex number? Now complex number is, say, a complex number, say alpha is x plus I y. Okay, the imaginary part and real part. You know this thing. So this is the imaginary part, and this is the real part. Okay, so all know about it. So nothing to worry about. So now, what is the difference between this classical system and quantum system? Here, if we write it after bit, we write the classical system and quantum system. That idea should be clear before writing down the implementation. So in classical system, the system can be, system X can be in the cube bit. Bit is the system, say here, 0 or 1. Here, just without notation, I'm writing. Here, the system actually in 0 or 1 or both. Now the difference. That is simultaneously in both the state possible. That is simultaneously, that is the difference. And that is the power also. In both the states can be possible. Qubit. X is a, here X is a bit, here it is qubit. The system is qubit. So the system can be in both the states. So for example, if I give the example, if I do not, actually this is a story here regarding Schrödinger's cat. So if I just write down box is there, the box is open. Simply I say there's a cat there and a poison there. Okay. So suppose due to the effect of poison, the cat can die, right? So right now, since the box is open, we can see that is the cat is live, okay, alive. Uh, or suppose cat is dead. That we can see here. That the box is open. Cat is dead. But if the box is closed, you do not know that, simply to say you do not know in which state cat is. Cat is dead or alive or both. Means dead or alive. We do not know. Okay. So that thing actually in quantum computation we have to know about it. And later in the subsequent videos, our classes, we have to discuss about this, because we have to discuss on quantum superposition and entanglement and using some gates. So where we have ended here, that cat is dead or alive. So that thing, uh, say if I represent here, if I come back to this plot sphere here, so you can see there, this is a sphere, means three-dimensional figure, right? So x, y, z. Okay, z is for the that is vertical one. You can see x is there and y is also there. So here you can see that qubit 0 is represented and qubit 1 notation is also there, right? So what is z-axis? Actually, this gives the probability of this. So now this thing is not right. Now it's clear what is the probability of a state where we have ended. Alpha 0, this thing and this. This some coefficients are there. Okay. The same there can be in b dot this. So probability of a state should be, we have to know first. Then we can go for this understanding of this superposition. So let me write down again, rewrite this state psi alpha 0, this, and alpha 1. Okay. So here you can see that here two coefficients are there in front of these two, 0 and 1 state. So alpha I have written, these are actually complex coefficients, and the property is there. So the property of this is here alpha square and alpha 1 square should be 1. Okay, so I'll give you some example. But this is the constant. This is the, you see, this constant is there. Alpha square and this. What is alpha 0 square? Alpha 0 square is the probability of occurrence. Probability of 0 state. And alpha, similarly, alpha 1 square is the probability of 1. Okay. Say the state is, sorry, say the state is 0. So in case of 0, we know this is 1 and this part is 0, right? That means probability of 1 is of course 0, not this one. Probability of 1 is 0 and probability of 0 is 1. Okay. And you know that is the probability, this constraint should be satisfied always. The total probability should be always 1. Okay. So this thing is there about probability. Now, if I give you one example with this probability, say I am going to write some new states. So this state is say plus state minus state. These are some quantum states. Plus state minus state. What are these? There's also other states, Bell states. So first basic sample we want to discuss is plus state. 0 and 1. This state is represented with this and minus state is represented with this. Say any arbitrary state. Okay. This will be actually here. So, 1 minute. This minus half root 1. Okay. Now, what is the probability of 0? For this case, say let's discuss about plus first. The probability of 0 is probability, say if I write probability of 0 is the square of this coefficient, this half, and probability of 1 is square root of this 1 square of this 1 by 2, the second half, and the sum is, you know, if we add these two, it will result to 1. Total probability of 0 and 1 is should be 1. Okay, we know the total probability of the total probability of all the outcomes will be 1. We know about head and tail. We know about bias, unbiased bias. Say in case of unbiased bias or unbiased head or tail, so probability actually half. Okay, you know. But if it is biased, so suppose any probability is something not equal to greater or less than half. Okay, so this probability we are actually have to measure, because here again I am saying coming back to this point, so that actually 0, 1 or both. So either if it is 0, so that means probability of 0 is 1. If it is 1, probability of 1 is 1 and the probability of 0 is 0. But if it is both, that is in superposition state. So now I think you have got a little bit of understanding. So in case of superposition state, so you can see that is, if I write here separately, superposition state, okay. So occurrence of here 0 and 1 equal. Okay, so that thing you have to know here. So occurrence of 0 and 1, and suppose probability of 0 is something and probability of 1 is something not equal to 1 or 0. So that you have to. So it is not always probability of 0 is always 1 or 0, and probability of 1 also, you can see here in this case plus, probability of 0 is half and probability of 1 is half. Okay, some other example, Bell state we'll discuss later. So you can see also that probability of some states or something, and probability of 1 also, not always 0 and 1. Okay, so that probability is measured in this way. So that is the main thing. If you cannot fully grasp it right now, but at least you have understood that how to calculate the probability and the measurement of this state, that is actually required. Measurement of the state psi. Okay, how to measure the state. So this is actually done by this, in this way, you can say. So 1 minute psi. Okay. So this is actually known as Euclidean norm. So how to measure this? So here I can write here in place of this here, sigma, you can say sum of this square and this root. Okay. So in this case, this square root sum of I is equal to 0 and 1 here, 0 to 1. You can see, go back to the previous slide. This slide say, okay, let me write down this again here, alpha 0 and alpha 1. So alpha 0 square and alpha 1 square. Okay. And this is known as Euclidean norm. Okay. No, nothing to worry about. But these notations were required. But mainly, I think you have understood how to measure the for a state, say plus, how to measure the state of probability of the state 0 and probability of 1. So if you recall this thing to calculate the states of probability of states of 0 and 1, so you can try it. Now I will help you with this thing so that you can solve the homework. So that thing I think you can do. Okay. So here in case of what is yeah, minus 1 by root 2. Okay. And 1 by the same. Okay. So now tell me what is the probability of 0. Actually it is written as like this way, or within bracket. So this is actually square of this half. And again I think you can understand minus of 1 by root 2 whole square is again half. So in this way, you can, if you anyone asks you, so you can calculate the probability of the states. Fine. So next, before discussing some operations, let's do again some simple things like uh, the gates, quantum gates. So you know about NOT gate. So the same thing is here. So basic gate of basic quantum gate is our NOT gate. So if you provide 0 state, it will be 1, and if you provide 1, it will be 0. And what is C0 gate? So this is the thing, C0 gate. Okay. So this is the control and target. Okay. First one, that is the dot one. And this is the second one, is the first one is control, and this is actually the target one, right? This is the target. So you can see control output is actually no changes there for control input X, and then control output same, no change there. And for Y, the output is actually depends on X. So how? So let's explain it here. So I'm discussing. So till there, if there is any question, you can ask me here directly, or you can unmute yourself. And this is a very beginning, so do not think the question is very silly. So, but please ask, no problem. So we are discussing about C naught gate. Okay, this is the thing. It looks like this. This is X, this is Y, and this is X or Y, right? Let me write. So what we know the XOR operation. 1 1 and 0 0 0. What is the XOR of this? The XOR of this. 1 1 and 0 0 0. Exclusive or XOR is actually like or let me write here XOR operation. So in case of OR, just I'm writing OR operation first. OR. So 0 1 is actually first 0 0 0, and else it will be always 1. Always 1. But in case of XOR, exclusive OR means that if in case of if both are same, then only both are different, then only 1, and if both are same, then it will be 0. If both are same, then it will be 0. Okay. So in case of OR, it is actually we say this is both, right? So if any one or both are true, then it is 1. But here both is actually not applicable in case of XOR. So if both are actually different, then only 1. Fine. So here, if the target x is target, so if x equal to 1, okay, 1 means I am talking about this 1 state, 0 state. So let me write simple as 1. So whatever the y may be, but actually it is actually effective. Okay. So this is actually 1 XOR y. Can anyone tell me what is the output of this 1 XOR y? Anyone? 1 XOR y. What is the output of this? Those who are actually first year, second years, they will face difficulty, but others, what is the output of 1 XOR y?
Y.
Try it again. Why not? Right? Why not? Why not? Because I do the calculation here. If y equal to say 0, so it will be 1. If y equal to say 1, that will be 0. So that means the inverse of y. If y is 0, then 1, and then this. So this is y not. Okay. So, but if x equal to 0, what will happen? XOR y means 0 XOR y means nothing but y. That is y, whatever the value of y, it will be the same. That is no effect of x if x equal to 0. I am writing in the next slide better if I write in the next slide. Just give me a minute. Yeah. So if I write that is here again, C not get here, just what we have mentioned, that when x equal to 0 and when x equal to 1, when x equal to 0, then um, output is same. There is no effect on x. But if y equal to 1, the target output, better to write target output is inverse. That is effective is there. If x equal to 1. So x should be, the control should be 1. That's why the name is controlled not get. So again it is inverse. That is not. It is performing inverse or not operation, but controlled by someone else or controlled by some other qubit. There's two actually here qubit. So we can confuse that we have discussed one qubit system right now. So 0 or 1. So what actually now 2 qubit system or 2 state or 2 qubit system. Very simple. Just if I draw the classical part again. So there is a system x and y. Say x, the states are for x, the states are 0 1, and for y again the states are again. This is a quantum or classical beat, whatever you can understand. Say for beat right now. Okay. say for bit it is 0 1. But now for this pair, if this is two system, two bit system, so the states will be the Cartesian product, the ordered pair of this Cartesian product of x y. Like so, it is I can write here 0 sorry 0 0 0 1 1 0 1 1. Okay, so you can easily say what about 3-qubit state. Okay, so this is the thing. So the first qubit system, quantum system I have presented here. This is, and the gate operation is there. Okay, so 2-qubit system I have written here in this way. So if the question, anyone asks you the question, what about the 3-bit system? Okay, so the number of states will be, I think you can you can tell me number of states. How many states? Tell me. How many states? 8 states, right? 8 states. 000 up to 111, right? X, Y, Z, Z. So in this way it is done. So now, since we have learned, acha, 1 minute, bit I have said. So same thing is goes for qubit. I have said whatever single bit system, I have done the same thing for single qubit. Here also for 2-bit system, whatever we have done is same representation goes for 2-qubit system. Same representation goes for 3-qubit system. In this way, okay. Actually, we cannot deal with just 1, 2, 3 qubits. We need more qubits. IBM next classes we'll be discussing how many qubits IBM provides to us for free, and how many for our paid channel you can access. Okay, but for free we cannot use the paid. Generally, we access the open one, and that will be using. So how many qubits? And that is not actually open access actually that are free to us. That actually limited. We cannot use too many qubits. Okay. We use simulator, we use hardware, but whatever. So we cannot use too many. Okay. So now the discussion up to 3 bits and qubits is actually there. So we can discuss topology gate or CC not gate. Okay, this is known as controlled, again controlled not gate. That is controlled by 2. So there are 2 control qubits. X is one control qubit, Y is another control qubit, and Z is a target one. So you can see there is an AND operation between X and Y. So if both are 1, in the previous case only X1, X was 1. But in this case, both should be 1. Otherwise, the AND product, AND is actually, if both are true, then it is output is true. So if both X and Y are 1, then only XY, this AND of X and Y will be 1. So both X and Y should be true. Both the control units should be true. Then Z will be inverted. Again, it is not, but controlled by X and Y. Similarly, Y is again being inverse, like not, but it is controlled by X. When X is 1, then only not, otherwise the same as Y when X equal to 0. Similarly, when X 0, Y 0, or both 0, no effect on Z. But when both are 1, then Z will be actually inverted. Okay. So actually, the time actually I am taking around 1 hour. Just within few minutes, I will be closing this. Too many things actually. Maths is very enjoyable. So at least I think this notation is clear. That will be. I'll be happy if these notations are clear. So you can write in the chat also if any doubt. So Discord channel is there. We can discuss later, and we can take any or at any time we can discuss, or we'll be live here the Gmeet. Just for the last one, this circuit. Okay, using one circuit, half adder circuit. If you have learned about this half adder circuit, so this is the circuit. So actually, this is a class quantum circuit, but the classical circuit is actually different. We are not going to discuss here. So this is a quantum circuit. You can see 2 gates are only used. One is Toffoli, CC not gate. The name Toffoli, please remember Toffoli and CC not gate. And the code will be discussed tomorrow. So please study this. and one is topoli here in the half adder, and in this here is one C naught, right? So let me say how it's actually, if we have heard about half adder. Right now we are not discussing half adder and the performance of this, but as if we are assuming this is known, say the sum is A or B and carry is AB. So let's see how it is actually, it is working or not. So this three lines, three wires here, you can see ABC. Okay, so okay, and this one, uh, right? Okay. So let me say first sum. Okay. So I'll write. I will not, since it is here. So you can write this thing. The sum equal to, in your copy you can write. So we have to show this is actually the value of sum is like this, and what is the value of carry, which will be like this. Okay. Say first discuss carry. That will be easy. One upon x2. So here these are controlled. So that means it is simply AB XORs. Okay, let me write here AB XOR C. Okay, AB XOR C. So you can find this here AB XOR C. Okay, that's fine. Now in this case, okay, let me write here first AB XOR C. Here in case of half adder, AB are the two bits here. Actually, one is 0. So since C is 0, what is this? Simply AB. So since C is 0, it is nothing but simply AB. So which is our carry. Which is our carry. Okay. Now sum. So here in this output here, no change because there is a control. There is no gate here. So only change will be here. The change is here. A XOR, sorry, A XOR B. Okay, A XOR B. A XOR B. In this line of B, for this B wire, so here in this here only one gate is there, which is C naught. So what is the output? Just we have learned A XOR B. Okay, so here this thing is. So I have not shown full adder. So you can show me. You can in the Discord channel you can paste the snapshots. Okay, in the general discussion. So or yes, in the general discussion you can put the snapshot of full adder. These are the some references you can study. But right now it's actually uh, better to discuss or study this thing, this gates, because we will be starting next day. Next day we'll be discussing the code of this, how to code this NOT gate, C NOT gate, and topology gate. Okay, so please study this. It will not take too much time, and a few simple questions will be there based on these gates uh, and the measuring probability. Okay, inner product, outer product, like this. So just 3-4 questions will be there, but please mandatorily, if you are wrong, please do not follow it. All are learning. Okay, there is no marks, 0 marks, highest marks. No, actually competition is going on, but for attendance or certificate purpose, we have to do this. Okay, so please try full adder if possible. Uh, Tomorrow we'll be meeting. So how to install? Please, I suggest you that tomorrow will be when you be watching this video, please open with your machine so that during that time you can try to install, or you can. They will also show how to use the simulators or cloud environment. Right? Actually, on cloud, simulators will be using on machine or cloud. So better if you cannot install within that time, you can use the cloud environment that you can use. Yes, if you have any question, I am stopping here. But if you have question,
So, hello. Yeah, Debashis sir is here with us now. So, sir will be sharing few words. Hello, sir.
Can you hear me? Am I
Yes,
audible? Okay.
yes, yes.
Yeah. Good evening, everybody. So, one nice talk by the previous, I think Suman Chakraborty is our research scholar, right? So, a very
Yes,
nice
sir.
talk. Uh, so, very nice talk by Suman. And you got some idea about this quantum computing, right? So, hopefully, this is a 2 days workshop, right? Tejas? It is
Actually, it will continue till the weekend. This week it will be.
okay. So, I mean, Saturday and Sunday, both.
No, sir. Actually, it is started today. It will be actually week-long program. So it will end on next week Monday, sir.
Okay, okay, fine, good.
Yes.
So, then I think I need not to repeat those things. I mean, the basics of the quantum computation already all of you know, and very nice presentation. And I think those scholars are much better because they are working on this field. So, fine. Then I want to just allow the screen. Screen. What happened? Okay. So let me state one thing, few words about this quantum. I am really very limited. I have very limited knowledge about this quantum things. Uh, so apart from the name quantum, I think all of you first year students, at least you already know what does it mean, the basic idea of the quantum mechanics, right? So I think you have that idea, right? Quantum mechanics actually it is a if you see yes and no, between this yes and no, some kind of if I take another state, okay, some probability of yes plus some probability of no. So that kind of superposition actually you are tapping, and you have this idea. I mean those terms like qubit, quantum entanglement, superposition, those keywords already you have heard and they have most probably explained. And this superposition property of quantum mechanics used for your qubit part, which is used for your computation. Similarly, the entanglement property of the quantum mechanics is used for quantum communication, and that way another field of quantum communication is has been evolved, right? But what actually this quantum computation, I think your organizers have requested me to say something about its effect in our social life and those parts, right? Really, what does it mean by quantum computation? Why it is this much so important? The thing is, okay, whatever we are doing 100 years back with pen and paper, now we have computers. So the same things or some much more things, much more faster way we can do, right? Similarly, once these quantum computers will come, we know that okay, much more faster way we can process what is taking around 100 years nowadays or 1,000 years within a fraction of second or within a minute it can be done, right? So that's the major advantage of this quantum era, correct? And have you thought ever all those tasks what actually discussed to be done or uh, will be done in much more faster way within fraction of seconds or those things, what kind of tasks are they? Means kind of task means I want to say the nature of those computations. Okay, task means for us it is computations, right? uh, what type of tasks people are discussing about those things, means which will be faster, will be computed in faster way? Any idea from your side? if you see, okay, for one example, suppose one 10 lakh bit, 10 lakh by 10 lakh matrix, you are multiplying with another 10 lakh by 10 lakh matrix. So if you do it in normal computer, it will take huge time. If you do in quantum computers, it will be much more faster way. But if I am giving you enough time, you can solve this 10 lakh by 10 lakh matrix multiplication, right? It is not impossible. It is impossible with respect to the time and given resource, correct? Are you getting the idea?
Yes,
So,
sir. Yes, sir.
so that means the tasks or computations what uh, are targeted here, they are by nature deterministic. Means, what does it mean by deterministic? Deterministic is such a thing that which will can certainly be done. Okay, it may take very large time, very large space, higher resource, all those stuff. But it is not impossible. Impossible with respect to the time, given time and the resource. So that actually the quantum computers will facilitate us to make it much more faster way. So if um, I want to share one thing with you, but I don't know how I am not able to sharing this one. Uh, but there are some problems or some computations are there which are by nature non-deterministic. Can you give one example? One simple example is if I tell you, um, say the number of values, okay, number of values within 1 and 2 real values, how many values you can say? Infinite, right? Correct. So one can say 100, another can say another 200, another can say another 1000, whatever. But practically it is infinite, right? So there is no deterministic solution for this one. So few problems are there in mathematics as well as everywhere, which are by nature non-deterministic or probabilistic. Or sometimes you can get a value, or sometimes it is you can't get a value, right? So these type of problems are non-deterministic, and in those cases, really, really, quantum computers can't do anything. What the classical computer can do, in that case, quantum computer also can do that part. Okay, understood the nature of the problem. So whatever you are, no, I am not sharing any screen. Let me share. Just I will share one document. Just anyhow, the idea is that few problems are there still. If you think if tomorrow quantum computers are coming and you can solve everything, that is not true. Some problem, some problems are there which are my talk. So few the problems which are by nature deterministic, that actually will be useful for quantum computation. Okay, and all those stuffs related to that quantum computations you already know. So, um, but few problems are there, like examples. So those problems in mathematics, they are called NP complete problems. Okay, that means the solution of those problems are non-deterministic, and if I got a solution that can be verified with the polynomial time, like if I tell you 1.5, okay, you can verify it that this is a real value between 1 and 2. If I tell 1.75, you can verify that it is between 1 and 2. That can be done. But if I tell you, uh, you tell me the total number of real values between 1 and 2, it is not possible, right? Uh, so in this way, you have to think where you have to apply your quantum computations, right? So blindly you should not select, okay, some everywhere I will apply uh, quantum computers, right? Yeah. So few problems are there uh, in our respective domains. Like if you see in uh, if you see in one minute, please. So so I think my screen is visible, right?
Yes, sir.
So this basic quantum computation, everything is described all those previous speakers. Qubits, quantum superposition, which is useful for this quantum computing, then quantum entanglement, which is useful for quantum communication, then the related gates, the comparison between classical and uh, quantum computing, and you have to select your problem such a way that the problem is solvable, frankly speaking. So if the problem is solvable, if enough time and resource are given, then only there the usefulness of the quantum computer is visible, not everywhere. Fine. There are so many NP complete problems, like in each of the fields, right? In lattice, everywhere. So many in mathematics, so many NP complete problems are there. If the problems, hopefully, most of you have the idea of this NP complete things. I don't know. Maybe the first year students don't have. The NP complete is N for the non-deterministic, means random in nature. Solution is random in nature, and the P is the polynomial verification. Means if you have a solution, then you can verify it, but you cannot get the solution with polynomial time. It is random. So by keeping all those things, some key milestone in our uh, quantum computation. So this is started with the development of the quantum mechanics in 20th, early 20th. Then when the
physicist Richard Feynman actually in 80s proposed the idea of this quantum computer. From there itself, the quantum computing got really a major thrust. And till date, actually, few achievements are there, like those IBM in 2016, IBM Q, Google's IBM, I mean, Sycamore in 2019, and during the last one decades, actually, some kind of development are there to improve the scalability and uh, for the building practical large scale quantum computers. But still, it is actually under question mark. The major issue is that the realization of those hardwares in normal state is a big issue. Uh, Fine, I am not going to that end. Let us come to the application wise. Application wise, it has huge application. Obviously, it will get huge application in the artificial intelligence and ML, machine learning. The reason why again it has great impact on those things, because if you most of you are quite familiar with this artificial intelligence algorithms and machine learning, right? So many CNN, DNN, deep learning, those models you are using. So you have, hopefully you have seen, right? So many times if you need much more data and much more nodes, much more layers, so it needs a huge time and huge resource, right? So that's the point where the huge time and resource are required. There, your use of quantum computer will be really helpful, and obviously it will change the paradigm. Similarly, uh, in cryptography also. So if you see, as I am giving a good example in the cryptography, because I am personally working in this field. In cryptography, today's cryptography, if you see those RSA algorithm and all those elliptic curve algorithms, so uh, you the what the idea behind the security there? The idea is that prime factorization of a big number for RSA, if we consider the RSA, right? So if I give you a 10-digit big number, and I am telling you factorize in two prime numbers, it will take really a considerable amount of time for you to get the things. But is it impossible if the like for 20 I mean 21, 7 into 3, right? 21 can be factorized in prime numbers, 7 into 3, correct? 39 can be factorized in 3 and 13, two prime numbers, right? But it is not impossible, right? It is deterministic in nature. There is a solution, but if I am just increasing the number from 39 to a 10 digit number, then it is really time consuming matter, right? So that's the idea there. For the searching part, you can easily use, if you use the quantum computer, it will take fraction of seconds. And the security belongs, for today's security, based on this RSA, most of the uh, areas this RSA and other symmetric cryptographies are used. So they actually believe that if I can give enough big numbers to factorize, so within a due time, suppose you are doing one transaction of within 1 minute or something, it is not possible or very less likely to get the solution within this 1 minute of time. So that's the philosophy of today's classical cryptography. Fine, but the issue is that they are not impossible to solve. They are solvable. That means by nature they are deterministic. Similarly, uh, but if you can give some problem to them which is non-deterministic by nature, so if you can use any higher end classical computers or any quantum computers, that doesn't matter, right? Because if the problem is not solvable, or with a certain probability solvable, means non-deterministic in nature. So you can't say that my quantum computer will be able to solve it, right? That means during the quantum era, even if you want to solve, if you want to give the security, from the security point of view, I'm discussing, you have to select some, either you have to select some problems from the mathematics which are non-deterministic by nature, or you have to use some kind of quantum encryption based algorithm. Okay. Another example like drug discovery and pharmaceutical research. So in molecular, the in genomic and molecular sequencing, they take huge time to sequence one species genomes, right? And there are so many combinations, huge number of combinations are huge, but it is huge, but it is not infinite, right? So in that sense, if you can get enough time and enough resource, you can get all the solutions. So obviously, quantum computers will help you there. In finance, there are, if you, for example, if you go for a stock market prediction, right? Uh, if you know 10 parameters of a stock, but actually there are 1,000 parameters for that stock. So if you can tap those all the 1,000 parameters, okay, computation will be very high in volume, but it can be solvable, right? So this way, the effect of quantum computation will be in our life to ease, to make easier those computationally intensive problems. Mind it, the problems are computationally intensive, those problems are easily will be solvable. That is correct. But some problems will remain ever, which are by nature non-deterministic, which cannot be solvable even by the quantum computation. So this is one part of the quantum era. Another part is this quantum entanglement, which is called the quantum, which is actually using in the quantum communication. So entanglement means if one state is known, its entangled state is also known. So in that way, some communication theory people are developing. But there will be another hurdle. Hurdle is that this today's classical communication can be easily implemented over either wireless or optical or wired channels. I mean cable, copper cables, right? But for this quantum communication, you need a specific dedicated quantum channel, right? Which is basically obviously based on the optical fibers and some specialized optical fibers. So that is another hurdle is there, that each of the communication from the end user to the server everywhere, you need that kind of specific communication. I mean medium, communication medium. Then only the actual quantum communication can be realized in practice. Okay, that is another problem with the quantum communication. But obviously, problems are there, people are there to solve, and some solutions would come, obviously. But whenever you will deal with any technology, I'm trying to say that the merits and demerits and its limitations both should be compared, right? So I think that's it from my side. Hope you have already got enough knowledge about this field, and other speakers are there, they will explore more in-depth things. Okay, thank you from my side.
Thank you, sir. Thanks a lot.
Thank you, sir.
Okay.
Thank you, sir.
Okay, then I think this is the end. So Good night to all of you. Actually, we'll be sharing the assignment by tonight, and you'll get 24 hours. Then within that window, we have to submit the Google form. That's it, and that will be posted in Discord only. That will not be mailed. Okay, so please follow the Discord channel. Okay, thank you all. Thank you.